reactivity difference actually qualify as polar covalent. So just something to keep in mind as we move forward. When we start chapter 10, we'll come back to this idea of bond polarity and apply it to molecules as a whole, rather than just between two atoms. We'll look at all the atoms in a molecule. Okay, so Lewis structures. We talked a little bit about how we take Lewis symbols and we combine them to form Lewis structures. We're going to now take that one step further and look at Lewis structures for more complicated things. We did water, we did CO2, we did nitrogen when we looked at double and triple bonds, but now we're going to build to things that have more than 2 or 3 atoms. So we need some rules. The first is that we're going to draw a skeletal structure of whatever our compound is, and we're going to put the least electronegative element in the center. Now, one caveat that I'll put here is that does not include hydrogen. Remember, hydrogen only has one s electrons, and so for him to have a full subshell, even a full n=1 shell, only requires 2 electrons. And so he can make at most 1 bond, because every bond is a pair of electrons. And so hydrogen will never be the center of our molecule, unless, of course, we're talking about a very simple molecule like H2. So we're going to put our least electronegative element in the center, and we're going to draw a sketch that sort of shows what the other elements are around it. Let's do what's a good molecule for us to do? Well, I'm going to do water again, even though we've already done it, just following these rules. So we put our element, least electronegative element, of course, other than hydrogen, in the middle. We're going to sort of draw this skeleton structure with all the rest of our atoms. We're going to count the total number of valence electrons. Only valence electrons are involved in bonding, and so we don't worry about the number of core electrons, only those electrons in the outer shell. If we have an ion, a polyatomic ion, we're going to add electrons for negative charges or remove electrons for positive charges. Now, each hydrogen comes with 1 electron, oxygen comes with 6 valence electrons, and so for us, that's 8 valence electrons. We're going to complete an octet for all atoms except hydrogen. For those of you who are musicians, maybe this is an easy one for you. Maybe this is 8 electrons. We talked a little bit when we did our Lewis structures on Friday, how every element that we had dealt with, except hydrogen, wants to have 8 electrons around it. That's because we mostly deal with things in n=2 and n=3. For n=2, to fill up the 2s and the 2p gets us to 8 electrons. For n=3, to fill up the 3s and the 3p gets us to 8 electrons. Those get us to that noble gas configuration. And so we're going to put an octet around all the atoms, of course, except hydrogen. He only needs 2. Sometimes we call hydrogen's electrons a duet of electrons. In this Lewis structure that we've already drawn, this skeleton structure, how many electrons are already around oxygen?
4.
4, that's right. We've got 2 in each bond and 2 bonds. So we need to add 4 more electrons around oxygen. There we go. And so that gives him a total of 8 electrons. Now that's all the electrons we have. Right? So we're never going to complete the octet if we don't have enough electrons, obviously. If we run into an instance where we don't have enough electrons, we're going to start forming double or triple bonds. Okay. One more quick example. If we do ozone, Ozone is the molecule O3. Since all those atoms are the same, it doesn't really matter what order we put them in, right? There's no least electronegative if they're all the same. How many valence electrons do we have in O3?
18.
18. 6 from each oxygen. Now I've already gotten 4 out of the way in these 2 bonds. Right? As we start to add electrons, we're going to add electrons to the peripheral atoms first, those atoms on the outside, and then the atoms on the inside. The reason we do that is because our least electronegative atom is in the middle. And so, as we assign these electrons, the atom in the middle is the one that carries the least. Now, that's a little misleading since all 3 of these are oxygen, but generally speaking, that's the rule we're going to use. And so we've got 4 already. I'm going to fill up the octet by adding these lone pairs. So that's another 6, that's 10. Lone pairs of electrons to these peripheral oxygen atoms, that's another 6. Right? So that brings us to 16, 18 total. I need a lone pair on that central atom, that central oxygen. That central oxygen only has 6 electrons. So we ran out of electrons. Not all of our atoms have an octet, and so we need to form either a double or a triple bond to the central atom in order to complete that octet. Now, because this molecule is symmetric, it does not matter one bit whether I pull this extra bond from the left or from the right. But what we're going to do is we're going to take a pair of electrons, a lone pair, and we're going to push those in to form a double bond. And so we end up with oxygen with 2 bonds to oxygen. And then I'm just going to fill in these lone pairs. Doesn't look great, but okay. Now again, it's symmetric. I could have just as easily pulled it in from the other side. That's a phenomenon called resonance, and we'll get to that later in chapter 9. Okay. So let's do another example. The Lewis structure for nitrogen trifluoride with all the fluorine atoms bonded to the nitrogen atom. Nitrogen trifluoride. Somebody give me a formula.
NF3.
NF3. Now it tells us all the fluorine atoms are bonded to the nitrogen atom. Of course, we should know that because the nitrogen is the least electronegative. We're going to put that in the middle. All the fluorines around it. How many valence electrons do I have?
26.
26, that's right. 7 from each fluorine, that's 21. 5 from nitrogen, 26. I've already used 6 in bonds. So there's 8, 10, 12, 14, 16, 18, 20, 22, 24. All my peripheral atoms have an octet. So I'm going to add the last pair onto my central atom. All my atoms have 8 electrons, so I should be satisfied, right? And so this is, in fact, the Lewis structure for NF3. Not too terribly difficult. Okay, I'm going to give you a minute to write out the Lewis structure for nitric acid, right? Hopefully you remember that this is HNO3. It gives you a little hint here that the hydrogen atom is bonded to one of the oxygen atoms, right? Rather than being bonded to the nitrogen directly, it's bonded to one of the oxygen atoms. So I'm going to give you just a minute to write out this Lewis structure, and then I'll draw it up as well. Hopefully you're starting with 24 electrons. Okay. So here I've used up all my electrons. That's 24. What's the matter with this Lewis structure?
Nitrogen needs an octet.
That's right. Nitrogen's missing his octet, and so we need to form a double bond. There's no difference if we do it from this oxygen or from this oxygen, right? They are equivalent for us, and so I'm going to take them from this guy and push in to form a double bond. Okay. Any questions on how we get that Lewis structure? Okay. Carbonates ion, CO3 2 minus. Again, I'll give you just a minute to work on that. How many electrons are we working with for carbonates?
24.
24, that's right. We've got 22 from the atoms and then 2 extras from this 2 minus charge here. So 24 electrons total, there's 6, so 8, 10, 12, 14, 16, 18, 20, 22, 24. My carbon doesn't have a full octet, so we need to pull in a pair of electrons to form a double bond. Again, it does not matter where we do it from. I'm going to do it from over here. Okay. All right, so now we have an ion. We need to do something to sort of make it clear that this molecule is an ion rather than being a neutral molecule. And so for ions, we're going to put the Lewis structure in brackets. So we're just going to put him in brackets like that. We're going to identify the charge. And just like we do with formula, we're going to put in the upper right-hand corner. So this is a CO3 with a 2 minus charge. Right? And so in order for a Lewis structure to be complete for an ion, it has to have those brackets and it has to have the overall charge for the ion. Okay. All right. So far, these have been relatively straightforward. The most difficult decision we've had to make so far is where are we going to put that double bond. But there are some structures that get a little bit trickier. And there's a tool called formal charge that helps us determine whether one Lewis structure is better or worse than another Lewis structure. Okay. Formal charge is sort of defined as this number of valence electrons in an atom, right? So let me be clear. This formal charge, Fc, is per atom right? Not overall. Right? A molecule will not have a formal charge. Each atom within a molecule will have its own formal charge. Okay. So the formal charge for any atom is the number of valence electrons for that atom minus the number of non-bonding electrons for that atom minus the number of bonds. Right? So just to be clear here, a single bond is one bond. Right? A double bond, even though it's in the same area of space, we still count it as two bonds. And of course, a triple bond would be three. The sum of charges in an atom, in a molecule or ion must equal the charge on that molecule or ion. So I am just going to redraw real quick. Oops. The carbonate ion that we had on the previous slide. Oops, and we're going to calculate some formal charges. So I'm going to number these oxygens. So for carbon, how many valence electrons does carbon start with?
4.
4. Now he doesn't have any lone pairs, and so he has no non-bonding electrons. And he has how many bonds?
4.
That's it. Okay. So 2 single bonds and 1 double bond counts as 4 bonds. And so our formal charge on carbon is 0. How about for oxygen? 1. Oxygen always starts with 6 valence electrons. How many non-bonding electrons on oxygen 1?
6.
6. And he's got 1 bond to the carbon. 6 minus 1 is -1. Oxygen 2, well, he looks mighty similar. Oxygen starts with 6 valence electrons. He's got 6 non-bonding electrons. He's got 1 bond. That makes him -1 as well. Oxygen 3 is a little different. He's got 6 bonding electrons. I'm sorry, 6 valence electrons. He's got 4 non-bonding electrons and 2 bonds. That makes him 0. Okay. So if I go in now and I write in our formal charges, carbon 0, oxygen 1, -1, oxygen 2, -1, and oxygen 3, 0. Okay. So this shows us 2 things. A, it shows us that we're doing pretty good with our Lewis structures because our formal charge should be as low as possible. Okay. So we have, we want to minimize formal charge as much as possible. Okay. And we've done that. Now we can't get them all to 0 because of what's in this box. Right? The sum of all the formal charges on the atoms within our molecule or ion has to equal the overall charge. So if we're talking about a molecule, they have to add up to 0. Since we're talking about this carbonate ion with a 2- charge, if we add all these up, 0 plus 0 plus -1 plus -1, we get -2. And so the charge of our ion matches the sum of our formal charges. Okay. Let's do another example where formal charges help us decide whether or not we have a good structure. So formaldehyde is the simplest aldehyde. That's a type of organic molecule. And it's CH2O. And so these are 2 different ways that we could think about drawing up that skeletal structure for formaldehyde. How many valence electrons does formaldehyde have?
12.
12, that's it. So in this one on the left, he's already used 6 in 3 different bonds. between carbon and oxygen, which of those is less electronegative?
Carbon.
Carbon. So I'm going to put the extra electrons around the oxygen first. So I end up with filling up his octet first. So that gives us a total of 10 electrons so far, 2 left over. I'm going to put those on the carbon. Carbon doesn't have a full octet, so we're going to have to push this pair of electrons in to form a double bond. Okay. So there's my 12 electrons. Everybody happy with their full octet. Okay. This other diagram, I still start with 6. So I'm going to fill the octet on oxygen first because he's more electronegative. I use up 6 more. So oxygen's octet is full. Carbon only has 6. So I'm going to steal 2 of those electrons to form a double bond with carbon. All right. So these two Lewis structures, they seem both legitimate, like they could both be reasonable. But we're going to take a look at formal charges. So since our hydrogens are the same, I'm just going to put them once here. And we will calculate, that's not a D, that should be an O. And we'll calculate the formal charge for our atoms. Hydrogen starts with 1 valence electron. He doesn't have any non-bonding electrons. He's making 1 bond. He's got a formal charge of 0. What's the formal charge of carbon in this left-hand molecule? Somebody walk me through it.
It has 4 valence electrons.
Yep.
And then 2 non-bonding electrons.
Yep.
And then 3 bonds.
And that gives us?
-1.
Right. All right. And then oxygen, well, he looks very similar, except he starts with 6 instead of with 4. He's got 2 non-bonding and 3 bonds. That gives him +1. So if we add all this up, we have a 0, we have a -1, we have a +1, and we have another 0. That does add up to 0. So, okay, it's all right for now. Let's take a look at the one on the right-hand side. Hydrogen, still 1 minus 0 minus 1, gives us a 0. Carbon starts with 4. He doesn't have any non-bonding, and he's made 4 bonds. That's a 0. Oxygen starts with 6. He's got 4 non-bonding and 2 bonds. That's also a 0. And so because all of our formal charges on the right-hand side are 0, this is the better Lewis structure. Okay. Now, again, they both have formal charges that add up to 0, but this is the better Lewis structure because the sum of the actual formal charges are all 0. Now, sometimes that's not possible, right? Sometimes we have to have formal charges that are not 0, even for a neutral atom. When that happens, however, which do you think would rather have this negative formal charge, carbon or oxygen? Now, in this case, carbon has it, but which of those 2 atoms would rather have a negative formal charge?
Oxygen.
Oxygen, why is that?
It's more electronegative.
Absolutely, absolutely. And so if we have to have non-zero formal charges, right, the negative or the most negative formal charge should be on the most electronegative atom. Remember, En is electronegative. Okay. And so even though for the structure on the left, even though all the formal charges add up to 0, it has sort of a strike against it because the negative formal charge is not on the most electronegative atom. Okay. On Thursday in lab, we'll do one example that there's only one way to do it, and it goes against this rule, but there's no other way to get the molecule to bond other than putting the negative formal charge on a carbon. So we've done this already for the carbonate ion, so I'm going to skip that one. And then just now that we've done a few examples, we will take a look at some rules for formal charges. And again, I mentioned some of these things. For a neutral molecule, like we just did with formaldehyde, right? Anytime that there are no formal charges, it's going to be better to ones that have formal charges, right? That's why we chose the one on the right. If we have large formal charges, so up to this point, we've always seen formal charges of plus or minus 1, but there are some Lewis structures that you could propose and have formal charges of plus or minus 2 or 3. Those are not as likely. Those are not as good Lewis structure as Lewis structures that have smaller formal charges. And so if we have to have formal charge, right, the negative formal charge should be on the more electronegative atoms. So again, just sort of going through what we mentioned earlier. Just briefly, I'll do carbonate one more time to reiterate this last data point. We said that the oxygen that was doubly bound was 0, carbon is 0, and then these two singly bound oxygens are -1. Again, oxygen more electronegative than carbon, so he would prefer to have those negative formal charges. Okay. All right. So now that we've talked about formal charge and about how that's one way for us to determine whether or not a molecule is reasonable in the Lewis structure that we've assigned it, we need to talk about resonance. Resonance is when there are multiple Lewis structures that have the same formal charge distribution. You know, maybe they're on different atoms, but it's still a plausible formal charge distribution. And there's no good way for us to tell whether or not it should be A or it should be B. I'm going to go back to the ozone one that we drew earlier. Ozone was O3, and we said that it had to have a double bond in order for all of the oxygen atoms to satisfy their octet, right? So here, all of the oxygens have a full octet. If we went and calculated formal charge, again, I'm going to label these 1, 2, and 3. What is the formal charge for oxygen 1? I'll assume you can do these now.
Zero.
0. How about oxygen 2 in the middle?
1.
That's it. I'm going to put a +1. And oxygen 3?
-1.
Okay. So this is an example of a molecule where we have to have some formal charges. We can't get away without having formal charges. And so this is the structure for that molecule. When I drew this, I sort of said, you know, this molecule is symmetric. It doesn't matter if I put the double bond on the left or the right. And that is a good indication that a resonance structure exists for this molecule. Right? Now, maybe you're saying, but he just flipped the molecule. He didn't really move anything around. What if I told you this is still oxygen 1, oxygen 2, and oxygen 3, right? And I did move those electrons around so that those bonds are in different places. If we go through and assign formal charges, well, now this one is -1 on oxygen 1, oxygen 2 still +1, and oxygen 3 gets a 0. These two are called resonance structures. And in order to identify a resonance structure, we have to draw both of them, and then we sort of draw this double-headed arrow between them. Okay. There is, you will not get full credit for a Lewis structure if you don't draw all the resonance structures, right? Because there's no one best way of representing ozone, right? The way on the left is not 100% accurate. The way on the right is not 100% accurate. We have to draw both of them. In reality, what happens is that that double bond sort of bounces back and forth over time, right? And so it averages out so that really there's 1.5 bonds on both sides. But we can't draw it as 1.5 bonds, right? Because we can't sort of split up our pairs of electrons. We have to have sort of a set octet around each oxygen. There's not a great way for us to demonstrate a bond and a half. Okay. Right. So that's a resonance structure. And so a fully correct Lewis structure includes all appropriate resonance structures. Now we will do an example where not all the resonance structures are the same, right? Some are better than others. In that case, you do not have to include them all, right? Just include the best one. But between the one on the left and the one on the right here, they're exactly the same. So we can't represent ozone with just a single resonance structure. Okay. All right, so carbonate was another one that we did. I just randomly chose the oxygen on the left, on the right, to be the oxygen with the double bond. But we know that it could be any one of these 3 oxygens, right? And so we can write in our double-headed arrow and move that double bond around. And because there's 3 oxygens, that double bond could go in any of those 3 positions. So we end up with 3 Lewis structures.
Do you keep the brackets around it?
Excellent question. I was just going to say, is this Lewis structure complete? And the answer is it's not complete because we still need brackets and we still need our charge. Okay. There are some references that I've looked at that put the brackets around each individual resonance structure, the brackets and the charge around each resonance structure versus the whole thing in brackets with the charge. To be honest with you, I haven't gone through and figured out if Alex really cares one way or the other. But if I do figure that out, I'll let you know. Right? To me, it doesn't matter a whole lot. Alex may be a little pickier. Okay. So there are 3 resonance structures for N2O. Right? So if our arrangement is in NO, work on that a minute, and then I'm going to ask you for what those three resonance structures might be. All right, Matthew, you're at the top of my screen. Give me your arrangement of bonds. That's all you have to give me.
Oh no, I'm kind of struggling with this. Arrangement of bonds.
So between nitrogen and nitrogen, what'd you end up with?
Nitrogen bonded to nitrogen, bonded to oxygen.
But is it just a single bond between nitrogen and nitrogen?
I got a triple bond,
Okay, triple bond here. And then between nitrogen and oxygen?
a double bond.
Ooh, how many electrons is around nitrogen now?
Oh, way too many.
Yeah.
Single bond.
Yeah, single bond. Let's keep it a single bond. And I'll go ahead and draw in some lone pairs of electrons. So that is one Lewis structure, absolutely. Who got something different?
I had a double bond around nitrogen and around oxygen.
Excellent. This is another Lewis structure. All right, who has one more?
A triple bond between nitrogen and oxygen.
That's it, yeah. If you didn't really come up with this one, it's okay because spoiler alert, it's the worst. But let's do some formal charge calculations, right? So for the first nitrogen in 1, 1, 2, 1, 2, 1, 2. For in 1, how many valence electrons does nitrogen have?
5.
5. This nitrogen has 2 non-bonding electrons and 3 bonds, giving him a formal charge of 0. How about in 2? He starts with 5. He's got no non-bonding electrons and 4 bonds. That gives him a +1. And then our oxygen, we've seen this arrangement before. 6 minus 6 minus 1 gives him a -1. And so we have 0, +1, -1. Our negative charge is on the oxygen. Is oxygen more electronegative than nitrogen?
Yes.
Yes. And so this is actually an okay Lewis structure. Let's see if we can do better. On the second one, for N1, we still have 5. We've got 4 non-bonding, 2 bonds. That's a -1. For N2, 5 minus 4 minus, sorry, 5 minus 0 minus 4 equals +1. And for oxygen, 6 minus 4 minus 2 is 0. So -1 +1, 0. Still not great. This one's not great because oxygen's more electronegative, so he'd rather have that -1 charge. Let's see the last one. I know I spoiled it by telling you this was the worst one, but for N1, we have 5 minus 6 non-bonding minus 1 bond. That's a -2 formal charge. Yikes. N2, 5 minus 0 minus 4 equals +1. He stayed at +1 this whole time. Oxygen 6 minus 2 minus 3 gives him a +1. Oxygen with a positive formal charge. Yikesy dikesy. Right? So 3 different Lewis structures. Which one of these is the best? Left, middle, or right?
The middle one?
Left.
Left.
Yeah, it is the left. Again, it's because oxygen more electronegative. So he's going to have the negative formal charge. And so this is the best structure. Okay. And so again, if this were, a question asking draw the best Lewis structure for nitrous oxide, you would not have to draw all 3 of these resonance structures because it's clear that only one of those is the best resonance structure for MO. Okay. All right. We're going to stop there for today. We'll talk about these exceptions to the octet rule on Wednesday. Like I said, we'll have a little bit of lecture Wednesday, but we'll do that exceptions to the octet rule and do some examples with those. And then Thursday, we will draw bunches and bunches and bunches of Lewis structures so that we get practice with this. Friday, we'll finish up chapter 9, looking at a new way for us to talk about the enthalpy of a reaction based on our newfound knowledge of what these different bonding patterns look like. Okay. So
Thank you.
yeah, I'll see you Wednesday again. It'll be a short lecture, and then if you have any questions, you can ask those.
Thank you.
Thank you.